Hello all. In this lecture, we will continue the discussion of method of solving first order non-linear equations. Here we use the method of characteristic equations, method of characteristic equations in extended form. Okay, so this is the third lecture in this regard. And in the previous lectures, we have formulated the characteristic equations. There are 5 equations, and when we solve these equations separately, we will get 5 ODEs. And for getting the complete solution, we need um, 5 initial conditions also. But from the so first of all, we start with the Cauchy problem, general Cauchy problem for the first order nonlinear PDE. So consider the first order nonlinear equation f of x, y, u, p, q equal to 0, where P stands for dou u by dou x and Q is the notation for dou u by dou y. With the initial conditions given by an initial curve gamma, which is a smooth curve and denoted by x is equal to x naught of s, y equal to y naught of s, u equal to u naught of s, where s is the parameter. And we know from the last lectures the 5 characteristic equations are xt equal to fp at x, y, u, p, q, and fq yt is equal to fq x comma y u p q, and ut is equal to p fp plus q fq, and pt equal to minus fx minus p fu, and qt is equal to minus fy minus q into fu. So these equations together with the initial condition, actually from the initial curve we get only 3 initial conditions. So we have to formulate, first derive an initial conditions for P and Q also. Then only we can solve this problem. And in some cases the Cauchy problem cannot be solvable, and some cases it may be it can be solvable, and this depends on the transversality condition. As in the case of quasi-linear equations, here is also there is a generalized transversality condition which gives the or which describes about the solution of the Cauchy problem for the first order nonlinear PDE. So before going to that result or that theorem, first we define the generalized transversality condition at a given point. Okay. So the definition is, let a point P naught stands for x naught, y naught, u naught, p naught, q naught at the point S naught. P naught be this point, satisfy the compatibility condition. Compatibility condition means these two conditions. Which are the two conditions? F at P naught is equal to, F means the nonlinear PDE. So F at P naught is equal to 0, and U naught dash at S naught means du naught by ds at S naught is equal to P naught into X naught dash plus Q naught into Y naught dash at S naught. So these two conditions are known as the compatibility conditions. That means for the differential derivative of u naught at S naught. Okay, this is the compatibility condition. And if in addition x dash into fq, x naught dash into fq, x naught dash means actually this is for dx naught by ds. Dx naught by ds. X naught dash at s naught means this at s naught is equal to s naught. Okay, so similarly, in the same way, y naught dash at s naught stands for dy naught by ds at s equal to s naught. Okay, so in addition, x naught dash at s naught into fq at p naught. P naught means this is the point P naught. X naught, Y naught is U naught, P naught and Q naught at S naught, minus Y naught dash into FP at P naught is not equal to 0. So this condition If this is satisfied, then we can say that the Cauchy problem means the nonlinear equation with the initial conditions. That means the equations 1 and 2 together known as the Cauchy problem for the nonlinear PDE. Okay, so for the Cauchy problem, we can say that this satisfies the generalized transversality condition at the point P naught. So a given Cauchy problem satisfies the generalized transversality condition at the point P naught if and only if x naught dash into fq minus y naught dash into fp is non-zero, should be non-zero. Then we can say that this satisfies the generalized transversality condition. So according to the generalized transversality condition, we can say that the Cauchy problem has a unique solution. This result we are explained in the next theorem. So consider the Cauchy problem. Cauchy problem 1 and 2. 1 to 2. Assume that the generalized transversality condition, let the condition be these two, let it be 3 and this be 4. Then there exists an epsilon greater than 0 and a unique solution. And a unique solution x, y, u, p, q in the parameters t, s for the Cauchy problem, which is defined for mod s minus s naught plus mod t less than epsilon. Moreover, the parametric representation defines a smooth integral surface u equal to u of xy. Okay, so this is the statement of the theorem. That means if the Cauchy problem satisfies the transversality condition which we explained in the definition, then there exists an epsilon such that the in this region, which region, mod s minus s naught plus mod t less than epsilon, for every epsilon there exists an epsilon greater than 0 such that in this region this equation, this problem has a unique solution. Which is the unique solution? X, Y, U, P, Q are in the parameters Ts. And moreover, for this parameters, we can change them into the required integral surface in the xy plane or xy. We can change the parameters from Ts to x comma y such that the required integral surface is u equal to u of xy. So for the Cauchy problem, in order to exist a solution, unique solution, the condition is that it must satisfy the transversality condition. Okay, so let's move to the proof. So in the first of all, we have formulated the 5 characteristic equations, and in order to solve these equations completely, we need 2 more initial conditions. That is, before we will have to find the initial conditions. P of 0s is equal to P naught s and Q at 0 is equal to Q naught s for P of Ts and Q of Ts. So in order to solve that 5 equations, we need these 2 also. And clearly, and we know that these 2 equations must satisfy at every point which conditions? The transversality condition. Okay, we have to choose P naught s and Q naught s in such a way that they must satisfy the compatibility condition and the transversality conditions, that at every point s. Okay, that is, it must satisfy the conditions. Which are the conditions? U naught dash at s naught is equal to P naught s into what? P naught s into x naught s plus q naught s into y naught dash at s, and the equation at that point x naught, y naught, u naught, p naught and q naught equal to 0. So this must be satisfied. And also from the hypothesis of the theorem, what was the hypothesis? We have taken that this satisfies the Cauchy problem satisfies the transversality condition at the point p equal to p naught. Or at s equal to s naught, this condition is these two conditions must hold, and we know, but we have to prove this holds for every point at s equal to s naught. And we know the one more condition that the Jacobian is not equal to 0, that is x naught at s naught fq minus y naught dash into fp not equal to 0, and the Jacobian of the system is not 0, doesn't vanish at s naught. Okay. Therefore, by the implicit function theorem, you can refer for the implicit function theorem for several variables, and using this we can derive that the required initial conditions for P naught and Q naught. So, from these two equations we can derive. We can say that therefore the implicit function theorem. Therefore, the implicit function theorem. Refer for what is implicit function theorem for several variables. Implicit function theorem implies that from these two equations at s equal to s naught, we can derive from 5 and 6 the required initial condition conditions for P naught and Q naught. Okay. Hence, the characteristic equations we now will have a full set of initial conditions in a neighborhood of mod s minus s naught is less than delta. Okay, so the characteristic equations with these initial conditions. Since the system of ODEs, the 5 ODEs, the characteristic equations is now well posed. Well posed means the problem is exists with the initial value problem. 5 initial value problems of the ODEs are there. 5 initial value problem ODE differential equations are there, and we have it is well posed, and by the existence and uniqueness solution for each of the initial value problem, we can say that there exists a unique solution in that neighborhood. Okay, that means we know that is that means from the first equation xt equal to fp, we can get a unique solution in the form x of ts, and similarly we will obtain from each equations what we obtained is the existence of a unique solution, unique smooth solution, smooth solution. Smooth means it is differentiable, belong to C1. Smooth solution. And from the first equation we get a x of ts, an expression for x of ts, and from the second equation we will get y of ts, and from the third we get u of ts, then and in the fourth we will get p of ts, and from the fifth last equation we will get an expression for q of ts, and we know that this is a unique solution because what's the reason? From the uniqueness and existence and the uniqueness theorem for each of the initial value problem. for t comma is guaranteed for t comma s in a neighborhood. In which neighborhood? In the initial value condition, in a neighborhood of the initial point, in a neighborhood of the initial point. Initial point is t equal to 0, so 0 comma s naught, initial point of t comma s naught. So in the neighborhood of 0 s naught, there is this problem has a Cauchy problem has a unique solution that we have proved. Now, as in the quasi-linear case, one can verify that the system of equations, the five system of equations, and this mm, and the initial condition for f of x naught, y naught, u naught, p naught, q naught equal to 0 at s naught imply that this is equal to 0. That means f at x of ts thus equal to 0. So as in the quasi-linear case, we can verify linear case, we can verify that the system of characteristic equations, the system of characteristic equations together with the initial condition, which is the initial condition. That means equation, which equation? Uh, where is the equation actually? Yeah, equation number 6 together with the equation number 6, this equation together with the equation 6 um, imply that what we get is imply that f of this will satisfy the equation. That means f of x of ts, y of ts, u of ts, comma p of ts, q of ts is equal to 0, where for all mod s minus s naught less than delta and mod t is less than epsilon. T means t minus 0 actually we are taking, so mod t is less than epsilon. And let this be equation number 7. Okay. So the first part of the proof is over. We have showed that there exists a unique solution in the parameterization t comma s for the characteristic equation. So for the Cauchy problem has a unique solution in the form x of ts, y of t, function of x of ts, y of ts, u of ts, p of ts, and q of ts equal to 0. But actually we need the parametric form in the xy axis or xy parameterization, or we have to find an integral surface of the form u equal to u of xy. So we have to convert the parameterization from t comma s to x comma y. Now such a parameterization is possible if and only if the Jacobian does not vanish. That means in order to prove that the parametric representation for x, y, u will define a smooth surface u of xy, we must show that the mapping in terms of ts, x and y in terms of ts can be inverted to a smooth mapping in terms of x and y. That means t and s we have to change in terms of x, y. Now such an inversion is possible if the Jacobian, this we obtain from the theory of functions of several variables. You can check the condition. Okay, so this mapping, or we can change one parameterization, an equation from one parameterization to another another parametric form or into xy plane or xy parametric equation if and only if the Jacobian of the variables is does not vanish or not equal to 0. So let's and here we have to find the Jacobian at the in the region of initial condition, a neighborhood of initial condition. So actually we have to show that Jacobian at the point 0 is not does not equal to 0. Actually we need to show this one. Okay, so Jacobian Jacobian at 0 comma s naught. uh, Jacobian at 0 comma s naught, we can find we can determine the Jacobian. This is actually by definition dou xy at dou ts at the point 0 s naught, isn't it? So this is equal to determinant dou x by dou s dou t t comma s, sorry, s comma t, we can write it as s comma t or anything. So dou s t, suppose we have writing this as xy in terms of st. If we are writing this way, we will obtain the Jacobian, determine the Jacobian as dou x by dou s, dou y by dou s, and the second column dou x by dou t, dou y by dou t at the point 0 is not, or this is equal to what? Xs at the point 0 is not into xs into yt at the point 0 is not minus xt at the point 0 is not into ys at the point 0 is not. Okay, again we have one more notation for this one. We have actually from the transversality condition, we denoted xs at 0 is not as dx by dx naught at the point is 0. 0 means initial condition, so initial value is x naught, so dx naught by ds at s naught, or x naught dash at s naught. This way this was the notation we used. So we can rewrite this as x naught dash at s naught into yt from the characteristic equations, second characteristic equation, we know that yt is equal to fp, so fq. So yt at the point 0 is not is actually fq at the point p naught, isn't it? So fq at p naught minus xt, similarly xt at y naught dash is, we can write it as okay, xt at 0 is not into or xt at 0 is not into ys at 0 is not, that is f okay, f p. Or fp, and the last inequality xs into ys at 0 is sorry, ys, similarly we can write it as ys at 0 is ys at 0 is not, so ys at 0 is not is actually y naught dash at s naught, so this is equal to y naught dash at s naught into, now xt, what is xt? Xt is equal to, from the first characteristic equation, xt is fp, and fp at the point at 0 is not means fp at p naught, and from the transversality condition we know this Jacobian. This is actually the transversality condition, generalized transversality condition, and from the hypothesis we have taken that The Cauchy problem holds the satisfies the transversality condition. That means this is not equal to 0. Therefore, the Jacobian at 0 is not equal to 0. That means that Jacobian does not vanish. So we can invert the parameters from t comma s to x comma y. So we have a smooth surface. Thus, there exists a smooth surface. What? Therefore, there exists a smooth surface u equal to u of xy. Okay. Now we need to show that this smooth function u of xy would satisfy the given Cauchy linear problem. That is the verification of this solution. Okay. For this, it is enough to show that the relations, that means ut and us, in terms of t and s. We have formed the solution in terms of x and y. Now we need to show that this the derivative with respect to t ut, and in terms of ts is equal to p of ts into xt plus q of ts into yt, and u in terms of s, that means dou u by dou s is equal to p of ts into xs plus q of ts into y of ts. So we have to show that these two equations would hold. Okay. Now for the first equation, look at the first equation. Ut is equal to p of t into xt plus uh, q of t into yt. This is actually, we know that the third equation, you consider the third characteristic equation. What was the third equation? Ut is equal to pfp plus qfq. This was the third equation. P means P at Ts, P of Ts into Fp. What was Fp? Fp is xt, isn't it? Xt at Ts plus what is Q? Q means Q of Ts into Yt. Yt is actually Fq. Fq at Ts. So from the characteristic equation. So this is from the third characteristic equation. We have ut is equal to this one. That means ut at Ts, ut at t comma s is equal to p of ts into xt at ts plus q of ts into fq at t comma s, isn't it? So we can say that our this equation is valid because our construction is in a such a way that this equation is satisfied. So from the construction, equations, um, from the construction of characteristic equations, it is clear that it is clear that the equation 9 will hold. Okay. Now we need to prove that the third equation, or sorry, the 10th equation us, that means the derivative of u with respect to s will hold. So we need to prove the 10th equation. For that, and we know US at 0 is, we from the transversality condition we know that the from the transversality condition, from the transversality condition uh, we know that this equation will hold at 0 is not, isn't it? Or 0 is, at 0 is. This will hold at a 0 is or 4 or at a t equal to 0 or at t equal to 0. But we need to show that this is true for all t comma s. For all t, we have to show this equation. We therefore define an auxiliary function sorry auxiliary function r of t comma s is equal to what is r of t comma ut minus um, p into xs minus q into ys. Okay, let this be equation number 11. Okay, so we need to show that what we need to show is, in order to show that ut equal to pxx minus qys, we need to show that r of t is equal to 0. Therefore, we need to show that r of t is equal to 0. And from the initial data for P and Q, it is clear that r at 0 is, that is when t equal to 0, this holds. That means r of 0 is equal to 0. To check to check r also vanishes for other values of t. For other values of t, we compute the derivative of r with respect to t. We compute rt. So r with respect to t. We have r is equal to, what is r? Ut minus p into xs minus q into ys. So this is our r. So rt is equal to, what is rt? U. So dou by dou s of ut. That means we can write it as ust minus, here we have to apply dou by dou s of, actually dou by dou s, sorry, dou t of sorry, this is actually us ആണ്. So ust minus dou by dou t of pxs. P means ux. P is equal to ux. Q is uy. Q is uy. So pxx, apply the product rule of differentiation. This is actually dou p by dou t. That means pt into xs minus p into xst. xst. Okay, in the similar way, we can find the derivative of qys with respect to t. So this will be, we can write it as pt minus pt into xs minus p into xst minus, now q into ys, qt into ys minus q into yst. Okay. So taking dou u by dou s. So rt is equal to dou by dou s of dou by dou s of ut minus dou by dou s of p into xt, isn't it? P into xt minus q into ys. Sorry, ys, not s, t, yt. But when we find but we know dou by dou s of p xt is p into xst plus ps into xt. One term is there, and dou by dou s of qyt, similarly q into yst plus qs into yt. So these two terms are missing here. So we can add that too also. So so in order to cancel those terms, we have to add that one. And here the remaining terms are, or no, plus we can write this as ps into xt plus qs into yt. Now the remaining terms pt into xs minus pt into xs minus qt into ys. Okay. And now again we can rewrite this as, now what is this one, ut minus pxt minus qyt, ut minus pxt minus qyt at t comma s, that we know that this is from the equation 9, this is equal to 0, this is equal to 0. So we can rewrite this as rt is equal to, what is the remaining term, ps into xt. We can write xt as fp. So ps into fp plus qs into yt, yt is fq minus mm, excess into okay, minus excess into, or plus excess into, we can write for minus pt, and from the characteristic equation we know that pt equal to fx minus p into fu. So minus pt will be, sorry, minus fx. So minus pt will be fx plus p into fu. So excess into fx plus p fu. Similarly, we can write for qt minus qt. So plus ys into fy plus q into fu. So this is our rt. Now taking fu terms outside, we can write it as fu into um, pxs plus q into ys, fu into pxs plus q into ys plus ps into fp plus qs into fq um, plus xs into fx plus ys into fy. Okay. Or rt is equal to, we can rewrite it as rt is equal to xs into sorry, fx into xs, fx into xs plus fy into ys plus fp, fp into ps plus fq into qs plus fu into pxs plus QYS. Now, from these terms up to this, we know that f of x, y, u, p, q equal to 0, pq equal to 0. And what is fs, or if f of, and that means in terms of t comma s, we can rewrite this as p of x of ts. Our solution was y of ts, u of ts, p of ts, and q of ts equal to 0. Okay, so we can find dou f by dou s, or fs. What will be fs? That means each variable, f is a function of x, y, u, p and q, but each x, y, u, p and q are functions of t and s. So fs will be, in order to find dou f by dou s, we have to apply the chain rule or differential form. That means dou fx into xs plus fy into ys plus fu into us plus fp into ps plus fq into qs. So this is actually fs. Now consider the right side of this equation with the right side of the equation rt, and we know that the term fu into us is missing here and all other terms are there. So we can write it as, we can add and subtract fu into us. So we can write this expression as fs. So for that we are adding and subtracting fu into us. So fx into xs plus fy into ys. I am adding here fu into us plus fp into ps plus fq into qs minus what, minus fu into us plus fu into the last remaining term pxs plus q into ys. Okay, now what is this one? Fx into, up to this we can rewrite this as, up to these terms we can rewrite it as fs. So fs minus, now taking fu outside, minus fs minus fu into what, us minus p into xs minus q into ys. What is this one? Us into pxs minus, we called it as r. So we can write this as rt is equal to fs minus fu into r. Okay, now we use the fact that fs, from the right side of this equation, f this equal to 0, we can rewrite this as this is equal to 0 or fs equal to 0. So apply that one, fs equal to 0, therefore we can write this as minus fu into r, since fs equal to 0 from the equation itself, from the solution itself. Okay. Right side is 0, so if s is equal to 0, we will obtain. Now consider this equation and let this equation be number, what was the number? Okay, 12. This is equation number 12. Okay, so from the equation we can consider this as an ODE, linear homogeneous ODE, isn't it? So we can write it as RT plus FU into R equal to 0. So this is a linear homogeneous, in the form of homogeneous ordinary differential equation. Okay, we know that this equation has fu is a smooth function and this is continuous. So by the existence and uniqueness solution, and we have the condition that r at 0 is, the solution of this equation is r of ts, and we know the initial value problem, this it is with a r of 0 is equal to 0. So by variable separable method we can find the solution as rt equal to um, rt means dr by rt means uh, RT means dr by dt is equal to dr by dt is equal to dr by dt is equal to what? Dr by dt is equal to minus fu into r, isn't it? So we can rewrite it as dr by r equal to minus fu into dt. So integrating, we can write r as e raised to minus integral fu into dt into c. Okay, so R of 0 is equal to 0 implies C equal to 0. So from this we can get that R identically equal to 0. So using that initial condition, we have proved that R identically equal to 0. That means the second equation, second derivative, second equation, that is equation number 10, also satisfied. Or us at t comma s is equal to p of ts into xs of ts plus q of ts into ys at ts. So the equation is so the solution is solution u equal to u of xy. U equal to u of xy is the required integral surface for the nonlinear Cauchy problem. Nonlinear first order Cauchy problem. Okay. So let's stop here. The problems we can discuss in the next lecture. Okay. Thank you. Thank you all.